on pages 88 and 89 of our textbook, Unit 3, Lesson 6, Exponential Function Basics. It'll be helpful if you had a graphing calculator and in addition to a regular pencil or red pencil. So today we're going to look at the basic components of exponential graphs and their behavior. Exponential functions, those whose exponents are variables. So when we're looking at an exponential function, the exponent is a variable. They're extremely important in math and science. So we have here y equals ab to the x, our basic exponential function, which is the same as y equals a times b to the power of x, where b is greater than 0 but not equal to 1. So when we look at y equals ab to the x, b here is referred to as the base. X is our exponent, or power, and a would be considered the coefficient. But in particular, b is the base. I will refer to the base quite often. Exercise number 1 asks us to consider the function y equals 2 to the x. So the base is 2. Fill in the table below without using a calculator, then sketch the graph on the grid provided. All right, so y equals 2 to the x. We're first putting in a negative 3 for x. So this is 2 to the negative 3, which is the same as 1 over 2 to the positive 3, which would be 1/8. Replacing x with negative 2, 2 to the negative 2 is equivalent to 1 over 2 to the positive 2, which is 1/4. And continuing, 1/2, 2 to the 0, 1, 2 to the first, 2, 2 to the second, 4, and 2 to the third, 8. Okay, I just want to put some numbers on our grid here before continuing. Now, sketching the graph. All right, so 0, 1, starting in the middle here, 0, 1, 2, 4, I skipped 1, 1, 2, back to that, and 3, 8, and negative 1, 1/2, negative 2, 1/4, and negative 3, 1/8. All right, so we connect these points. Nice smooth curve, and this is free-handed. It is not with a straight edge. This is free-handed. It's a nice smooth curve. And we notice here this base of 2. Our graph here is increasing. We're going uphill. This is increasing. Oh boy. And that's because our base was greater than 1. Whenever your base of an exponential function is greater than 1, you're going to have an increasing function. Exercise number 2, consider the function y equals 1/2 to the x. This is a different base. This base is less than 1. Using a calculator to help, fill out the table below and sketch the graph. I think I'll switch colors to green. I don't think I need a calculator. First, replacing x with negative 1/3. This is 1/2 raised to the, negative 3. To take care of the negative, I'd flip that. That'd be 2 to the positive 3, which is 8. And you can use the calculator, right? If you like, just go to y equals and key in alpha y equals 1 over 2 raised to the power of 3, nope, raised to the power of x, sorry, and then look at the table of values. There we go. 8, 4, 2, 1, 1/2, 1/4, 1/8. Same thing. Let me put some numbers down before I plot these points. So 0, 1. Well, that's common to both graphs. 0, 1. 1, 1/2. 2, 1/4. 3 1/8. And -1, 2, -2, 4, and -3 8. And we notice here, as we connect these points, that this function is decreasing. And that's because our base, which is the 1/2, is it's less than 1. It's less than 1, but greater than 0. Okay? Because our base is less than 1. What do they share? They have the same, both have the same y-intercept, 0, 1. Next, the horizontal asymptote is a horizontal line y equals some number. A function approaches this line as x goes to -infinity for growth. That's growth is when we're increasing. Or x goes to +infinity for decay. Decay is when we are decreasing. For decay, the base is going to be less than 1, and for growth, the base is greater than 1. As x goes to positive or negative infinity, y goes to the horizontal asymptote's value. Based on the graphs and behavior we saw in exercises number 1 and 2, state the domain and range for an exponential function of the form y equals b to the x. All right, so here we have the domain. Looking at the domain for each is, it's all real numbers, right? It's covering all real numbers. So the domain is all real numbers. Which I wouldn't write the words, I'd write the symbol, all real numbers, that or -infinity to +infinity. Right? In exercise number 1, as x goes to -infinity, y goes to, this is where you want to use your red pencil. All right, this is approaching 0. As we go, as this keeps getting smaller, as our x keeps going out to -infinity, our y values approach 0. I'm just going to draw a dotted red line. Y goes to 0. Y approaches 0. In exercise 2, as x goes to +infinity, right? As x goes to +infinity, this also approaches 0. This is our horizontal asymptote. A horizontal asymptote. Y goes to 0. Are exponential functions 1-to-1? Are they 1-to-1? The two that we have here? Yes. How can we tell? Pass the horizontal line test. What does this tell us about their inverses? Their inverses will be functions, or are functions. Now consider the function y equals 7 times 3 to the x. Determine the y-intercept of this function algebraically, justify our answer. Okay, so y-intercept, that's where it crosses the y-axis. That means the x input is 0. So we put 0 in for x. 3 to the 0 is 1. And 7 times 1 is 7. So our y-intercept is 7. Does the exponential function increase or decrease? Well, what's the base? Base is 3, so it's increasing, right? The base 3 is greater than 1. Create a rough sketch of this function labeling its y-intercept and its asymptote. Okay, so its y-intercept we know is 7. So I'm just going to maybe put a point here, 7, and we know it's increasing. We can look at it in a calculator if we want, but it's just going to be an increasing exponential function like this. Right, click y equals okay, I could have made it a little sharper than I did, which I think I'll fix. Make this a little steeper. Oh, labeling its y-intercept, which is there. 0, 7 is the y-intercept, and its asymptote. Asymptote is y equals 0. Consider the function y equals 1/3 to the x plus 4. All right, so this is a little different here. We definitely have a base that's less than 1, so we know that this is going to be decreasing. All right, but then we've got this plus 4 at the end. How does this function's graph compare to that of y equals 1/3 to the x? Well, let's look at it then. Okay, so we have y equals 1/3 raised to the x plus 4, and y equals the first one is in blue. This is plus 4. Okay, we know that they're both going to be decreasing because their bases are less than 1. And so this is, the red is 1/3 to the x, which has that same y-intercept of 1. And now it looks like the blue one is the same as the red but shifted up 4, right? And maybe you might recall something like that from transformations in geometry. Okay, so what does adding 4 to the function's graph do? It shifts it up 4. Determine this graph's y-intercept algebraically. Justify your answer. Okay, so y equals 1/3 to the 0 plus 4. Anything to the 0 is 1. So y equals 5 is our y-intercept. Now create a rough sketch of this graph, labeling its y-intercept and asymptote. So the y-intercept is 5. I'm just going to put some marks here. 1, 2, 3, 4, 5. And notice, so I'm looking at our blue, it looks like our horizontal asymptote, instead of being, the red was 0, if we move up 4, so the blue is going to be 4, y equals 4 is our horizontal asymptote for our function y equals 1/3 to the x plus 4. So I'm going to draw my red line first. This is our horizontal asymptote, which is y equals 4. And back to so as x goes to positive infinity, y approaches 4. And our y-intercept was 5. And let me just write down that, yes, this was, we knew that by these bases, these were decreasing. Thank you once again for your attention.